Several new technologies have begun to emerge recently, technologies that have the potential to dramatically reshape the investment casting industry. From casting and gating design to prototype wax production, these advances are destined to revolutionize the production of investment castings. At Sandia National Laboratories, we have developed an integrated approach called FastCast to combine these technologies into a program aimed at reducing the time needed to deliver a new investment casting and to make it better. The main elements of the program we will describe here center on solid modeling, the creation of an electronic design, rapid enmeshment, conversion of a solid model into a 3D mesh suitable for finite element modeling, computational technologies, the analysis techniques which use the 3D mesh to determine heat flow, fluid flow, and stress analysis, rules for casting, a combination of modeling and experimental measurements to characterize the filling of a complex mold. Free-form fabrication, the production of a finished wax pattern and gating assembly without the use of an injection die directly from the electronic design. Two promising methods of free-form fabrication are available for investment casting wax. The first is based on a process known as selective laser sintering. In this process, the electronic design is sliced into horizontal layers. These layers are then built up one upon another by the laser sintering process seen here. When complete, the laminations have been fused to form a solid wax model representation of the electronic design. A layer of powdered investment casting wax is spread by a set of rollers to a precise thickness. A laser beam is then rastered across the powder to sinter it into the desired shape. Once this step is complete, another layer of wax powder is deposited and the process continues with the next slice in the design. Each layer is supported by the preceding layer during production and then carefully laser sintered to ensure good bonding and sufficient densification of the wax powder. One of the major advantages of the SLS process is the ability to produce a wax pattern directly from the CAD system, thus eliminating costly tooling and lengthy lead times. The SLS system is shown here operating in real time. When complete, the wax part is simply removed from the powder bin and cleaned. A second process for die-less fabrication of a wax pattern from an electronic design uses a process known as fused deposition modeling. This process also separates the model into horizontal slices and builds the part by successive layering. A wax wire filament is extruded through a fine capillary attached to a numerically controlled XY positioner. A heater on the head keeps the wax just above its melting temperature. As the head moves along a path defined by a particular horizontal slice of the part, the wax is precisely extruded out of the capillary. Since it is only slightly above the melting temperature, the wax quickly solidifies after joining to the underlying layer. When a layer is completed, the supporting table lowers and the process continues with the next slice. After the final layer is deposited, the part is removed from the table. The selective laser sintering process is already being incorporated into Sandia's production of prototypical components. This wax pattern was produced entirely from an electronic design. FastCast is the development and integration of these technologies into an analysis toolbox to be used with the electronic design. The first step in this toolbox is the creation of a solid model representation of the part. This 3D model of the final object will eventually serve as the electronic data to generate the part by selective laser sintering. To perform analytical computations on the design, the solid model must then be converted to a mesh suitable for finite element modeling, a mathematically correct data file in a form that analysis techniques can use. Sandia researchers are developing an automatic system for rapid mesh generation called plastering and paving. Note that the mesh generation is fully adaptive, continually updating the mesh in response to features in the CAD representation of the part. The meshing program automatically generates the correct geometry around these more complex shapes. Once the mesh has been created, the design may be analyzed to predict fluid flow into the mold, heat conduction as it cools, and stress analysis as the metal contracts. An example of cooling by thermal conduction of a mold will be shown. Different colors represent different temperature ranges as the casting cools. The part illustrated here is shown starting at 2900 degrees Fahrenheit and allowed to cool to 1570 degrees Fahrenheit by radiative processes. This thermal model includes the effect of view factors, or the effect of one section of the part radiating heat to adjoining surfaces. With view factors, areas such as pockets remain hotter than would be predicted without their incorporation. The final piece of the analysis is the evaluation and optimization of a component and gating system for the casting process itself. To accomplish this, a series of experiments is being conducted with the goal of establishing rules for casting. These experiments are designed to watch the filling of a mold with X-ray images. Shown schematically here, the mold consists of a flat plate gated on one edge. An X-ray source shown above the plate provides the location of the metal front as the mold fills on the fluorescent screen situated below the mold. Thermocouples placed along the center line of the mold also provide temperature data as the mold fills. These tests provide the modelers with metal front velocities and metal front temperatures as a function of mold thickness, mold temperature, and pour temperature. In this first segment, the mold was kept at 1150 degrees centigrade. The pour temperature was 1700 degrees centigrade, and the plate thickness was 2 millimeters. The molten metal will enter from the left. Metal vapors, which precede the molten metal, can be seen swirling around the gate area just prior to pouring. The thermocouples used in the experiment can be seen as the array of features along the center line of the plate. Although only 0.003 of an inch in diameter, these thermocouples can be resolved with the X-ray image. In slow motion, the flow of metal into the casting can be easily followed. Turbulence in the metal causes several air pockets to form. These pockets are subsequently collapsed as more metal fills the mold. In the next experiment, the mold temperature was dropped to 1100 degrees centigrade. The pour temperature remained constant at 1700 degrees centigrade, and the plate thickness was reduced to 1 millimeter. Note the dramatic change in the gating system's ability to fill the mold. In slow motion, one can see how the metal flow is halted quite abruptly. The metal proceeds only a few inches into the mold before the leading edge freezes and the remaining metal is forced to the edge of the mold. The integration of these technologies will create an overall system to analyze and optimize a design and to characterize its response to a simulated casting sequence. Design changes can be incorporated and evaluated quickly and easily. Free-form fabrication allows waxes and castings to be procured in less time than is traditionally spent on engineering drawings. Although FastCast is an integrated program, each of the individual components represents significant advances and may have immediate applicability. An example of this is the set of fluidity experiments and subsequent rules for casting. In addition to benchmarking computer models, these rules can be used to directly aid the gating of a complex casting.
Research at Sandia is coupling design and manufacture. By merging robotics and CAD, or computer-aided design, we have created an integrated system that improves design while reducing product and process development times and makes robots practical in small lot production. Automatic programming and the use of sensors are the keys to using robots to their full potential in manufacturing. In Sandia's robotic edge finishing laboratory, the automated deburring system reads the Anvil 5000 CAD database and writes robot control programs. The robot can deburr parts in 1/10 the time of manual methods while providing higher quality. Other Sandia research in controls and sensing will allow robots to be used for high-speed light machining, reducing fixturing requirements while providing new capabilities, such as automatic compensation for tool wear. In the automated assembly laboratory, Sandia is showing how robots will be used to assemble parts. For assemblies like this strong link pattern wheel, a critical safety component, the prototype Archimedes system developed at Sandia uses the CAD model as the starting point for automatically developing robot assembly programs. The factory of the future needs to efficiently manufacture small lots and even one-of-a-kind items. Sandia's system paves the way by automatically writing the robot program and even designing additional fixtures needed for carrying out an assembly, eliminating the manual programming that limits current applications. The automatically generated plan uses computer vision to reduce the requirements for precise part placement. Misoriented parts are detected and the plan is amended. Other sensors, such as this 6-axis force-torque sensor, monitor contact forces, permitting fine adjustments in position. The Archimedes system has applications beyond robot programming. By using Archimedes to write programs for robot simulators, we can evaluate the costs of manufacturing different designs before the first part is made, making Archimedes a design evaluation tool. It becomes a facility planning tool when we produce simulations for different robots to see which can handle the job best. By merging the instructions output by Archimedes with the exploded diagrams it creates, Archimedes becomes the core of a publishing system for producing instruction manuals. Large, complex assemblies can take years to put together. Cost-efficient ordering requires the ready date for each part to allow it to be ordered on a just-in-time basis. Archimedes is capable of creating a bill of materials with part due dates, adding material planning to its capabilities. Economics will require that the same robot perform a variety of fabrication and assembly tasks. Research at Sandia will provide the factory of the future with work cells that can automatically reconfigure themselves according to current production needs, while advanced user interfaces will keep operators alert to system function and status. This research, underway at Sandia to support the need for building small lots of high-precision components in the weapons production complex, will also enable the aggressive manufacturer of the future to react to changes in demand on a continuous basis, rescheduling production location and product mix. Systems like Archimedes will speed the introduction of new products while reducing production costs, improving quality, and reducing risk. Rapid, economical response to changing conditions will be the hallmark of a world-class competitor.
A new form of supercomputer promises an order of magnitude increase in computing speed, the massively parallel computer. The processor is the device at the heart of the modern digital computer. It does millions of mathematical calculations each second and gives computing power to the lowliest personal computer and the fastest supercomputer. The concept behind massively parallel computing is to use many hundreds to many thousands of processors working together in parallel on the same problem. This approach appears to be the only way to get to the breakthroughs in supercomputing capability needed to ensure United States leadership in commerce and industry. But conventional wisdom has held that parallel processing on such a large scale could achieve only a modest increase in computing speed. In 1987, researchers at Sandia National Laboratories demonstrated that massively parallel computing with 1,024 processors could solve problems over 1,000 times faster than with a single processor. These basic techniques have been patented by Sandia. Specifically, Sandia demonstrated that when the problem size is increased in proportion to the number of processors, the speed of solution can also increase in proportion to the number of processors. The key was to change the thought process from trying to speed up a fixed size problem to scaling the problem size with the number of processors. This idea is called scaled speedup. Since then, Sandia has led the way in applying massively parallel computing techniques to real-world engineering and scientific problems. Sandia has established a massively parallel computing research laboratory in Albuquerque, New Mexico. It is one of the world's largest. This facility provides access to researchers around the world to the latest massively parallel supercomputers, such as the Thinking Machine Company's Connection Machine, CM2X, with 16,384 one-bit processors and 512 floating point processors, and N-Cube Corporation's N-Cube 2 with 1,024 processors, and also the recently added IPSC 860 from Intel Corporation's Scientific Supercomputing Division. Sandia also has a large team of experts that are pushing the frontiers of massively parallel supercomputing, researchers, programmers, engineers, and scientists, people who understand both complex research problems and massively parallel supercomputers. One current initiative at the Massively Parallel Computing Research Laboratory centers on medical imaging. In collaboration with physicians at Baylor University Medical Center, we are exploring the use of our CM2 massively parallel supercomputer to process their magnetic resonance imaging data to better diagnose arterial problems of the brain. Radiologists currently make diagnoses from conventional MRI scans by looking at a series of two-dimensional slices. The CM2's massive memory and computational capacities allows us to create whole image sequences, that is, movies, making better diagnoses. In another initiative, we have used massively parallel computers to focus synthetic aperture radar images faster than can be done on conventional supercomputers. Sandia was awarded a patent for the technique. Here, an initially blurred radar image of a solar tower facility at Sandia is iteratively focused until a clear image results and individual ground reflective mirrors are visible. Sandia is also leading a consortium of industry and academic research institutions to perform computer design of materials and molecules on massively parallel computers. These computations will be aimed at increasing our understanding of catalytic reactions, semiconductor growth, and metal alloys to the point that we can rapidly develop materials with specific properties. The crystal shown is a terraced aluminum surface for which the configuration has been determined by relaxing the atomic positions to achieve a minimum total energy using a quantum chemical simulation of the system. The terraces are the nucleation sites for further growth and absorption. Sandia researchers are developing a technique called paving to automatically generate well-formed finite element meshes in arbitrary geometries. Solving very large problems enabled by the new capabilities of massively parallel supercomputers requires generating large finite element meshes. Paving significantly reduces the time required to produce a high-quality, large mesh. Paving is particularly adept at transitions between various sized elements while maintaining reasonable individual element shapes. We developed a computer model on our parallel machines of the motion of a charged particle beam passing at nearly the speed of light through a background plasma. A few time steps of the simulation are shown here as the beam grows in length. These high-energy beams are studied experimentally at Sandia in our pulsed power research efforts to develop new fusion reactors. Another application of massively parallel computing at Sandia is computational fluid dynamics. Numerical simulation of fluid flow demands the world's largest computers as well as state-of-the-art numerical algorithms. In this simulation, a three-dimensional box filled with air is subjected to a cooler temperature on one side and a warmer temperature on the opposite side. Buoyancy forces give rise to a three-dimensional natural convection, which is displayed as the movement of two surfaces of constant temperature in the fluid. Only 64 processors of the N-cube 2 are needed to run this simulation at about the same speed as a conventional vector supercomputer. In other fluid flow simulations, Sandia is applying massively parallel computing to three-dimensional problems simulating the Kelvin-Helmholtz instability arising from the shearing motion of two fluid layers. With 8 million computational cells, such a simulation runs about 6 times faster on 1,024 processors of the N-cube 2 than on a conventional vector supercomputer. In addition, a third example, shown here, simulates the supersonic aerodynamic flow around a re-entry nose cone. The streamlines indicate the velocity direction in this three-dimensional steady flow. With 256 processors, this calculation generates the solution to over 64,000 unknowns. Massively parallel computers are also being used to simulate high-speed impacts. In this example, Sandia demonstrated capability to rapidly simulate a hypervelocity particle hitting a bumper shield. The first shields that are impacted shock the impacting body and cause material heating and expansion. This results in the impact being spread over a broader area. Researchers at Sandia have developed enhanced three-dimensional capabilities in this code to allow for elastic plastic and detonation modeling. The same code is also capable of simulating high-speed impact and penetration problems. Applying massively parallel supercomputers in the future will allow simulating the behavior of complex vehicles impacting safety-qualified structures and enhance our ability to predict the consequences of catastrophic impacts. Sandia National Laboratory's Massively Parallel Computing Research Laboratory has successfully demonstrated the application of massive parallelism to many complex problems. Our worldwide leadership in applying the speed of massively parallel computation can provide a competitive edge to a U.S. company bringing new products to market.
Scientists who've developed a new combustion analyzer say it could promote a burst of activity for the auto industry in its search for better ways to conserve fuel and cut down on pollution. Kathy Hart reports.
This looks like an ordinary spark plug, but closer inspection reveals 8 tiny holes around its rim. And when fiber optics are attached, they work like windows to actually see inside a car's combustion chamber while it's running.
This helps gain understanding on how the combustion process proceeds in the cylinder. So eventually it can lead to better ways of controlling emissions.
The commercial name for the seeing spark plug is the Barrick-Whitsey probe, named after Barrick Laboratories and the inventor, Peter Whitsey. Engineers first invented the probe to understand why so many cars experience rough idling. They used the Whitsey to get a high-tech picture of how a flame develops during combustion and how it's affected by air-fuel mixtures.
It's very microscopic, but what happens early in that flame propagation region affects what happens later on, affects the end of combustion. Does it finish in time? What are the emissions and what's the fuel economy of the engine?
And that's the final tightening.
This is how the diagnostic tool works. The spark plug probe replaces a regular spark plug. The blue wires you see are the fiber optic cables. They run from the spark plug probe to an electrical box, where the optics light signal changes to an electrical signal. That leads to this computerized picture of the actual flame inside the car's fiery combustion chamber each time the car ignites.
Well, it's telling us that the general direction of the flame is over in this direction relative to the position of the spark plug. So there is probably some turbulence blowing the flame in that direction.
The probe has caught the attention of a number of research laboratories as well as some of the big oil companies, but especially the American automakers who face increasing government pressure to build vehicles that are more fuel efficient and less polluting. Stephen Plee believes the probe advances beyond expensive laser technology or time-consuming photography.
The major advantage is it's non-intrusive, it doesn't disrupt the combustion process at all. It's very simple to implement and much cheaper.
With a price tag exceeding $1,000, the probe offers no direct use for consumer car maintenance, but researchers say its technical capabilities move them forward, not only in understanding combustion, but in controlling it.
This is the ion gap head gasket flame geometry probe as installed in a single-cylinder version of the GM 3800 engine. Here you can see the position of the 8 ion gap probes relative to the combustion chamber. The 8 windows represent the 8 ion probes around the periphery of the head gasket. This is a crank angle versus voltage trace for each of the 8 individual probes. What you see here is a voltage spike when the flame arrives at that position. You use this screen to set thresholds so you can identify the proper value that you'd like. And what the picture in the middle shows is then the time of flight from spark until flame arrival for the 8 individual head gasket ion probes. Up till now, our use of combustion diagnostics has consisted primarily of pressure-based diagnostics. The ion gap head gasket flame geometry probe gives us additional insight into the combustion process by giving us information on flame visualization rather than just pressure. We've already used it in a single-cylinder engine to detect differences in flame propagation between two different cylinder head ports. We intend to use it in the future to study causes of cyclic variation in the combustion process. Also, many other product teams at General Motors are interested in the use of this tool for combustion development.
That's engine knock. Automotive engineers call it the most serious design limit to developing a more efficient and powerful engine. A decade ago, lead additives in gasoline eliminated engine knock in most cases. But with today's unleaded fuels and high compression engines, the problem is very much alive. At the Combustion Research Facility of the Sandia National Laboratories, scientists are searching for a better understanding of the phenomenon.
Knock is a sudden pressure rise in the engine. It's not really clear what causes it. Generally assumed it's an auto-ignition process where the flame is moving across the engine and heating gases ahead of the flame, and suddenly, boom, the reaction takes off. That creates a sudden spike, and that tears up the engine.
To unravel the mysteries of engine knock, researchers are using what amounts to a specially designed lawnmower engine. Instead of 1, 4 spark plugs are fired simultaneously. A normal burn begins at 4 locations. Initially, the flames move away from each spark plug in a swirling pattern toward the center of the chamber. However, as temperature and pressure increase, the end gas suddenly auto-ignites, creating that unwanted ping, or engine knock. The cylinder head of the laboratory engine is a $3,000 piece of see-through sapphire, so that multiple laser beams can display what is happening during combustion, from ignition to knock.
We're looking at it from a very fundamental viewpoint to see what chemical species are present just at the beginning of knock, in the hopes that if you can identify what's there, you can add some chemical ingredient that will attack that molecule and get rid of it. And we've made a lot of headway in that.
The Combustion Research Facility here is the largest in the world and spends about $10 million a year. Currently, it's considered the leading such facility. But both Germany and Japan are now in the race to develop technologies that promise a multi-billion-dollar industry payoff in the future. Charles Crawford, CNN, Sandia Labs, Livermore, California.